Welcome to a new video of question number 6. So let's see what the question tells us. So P belonging to 1 to infinity, we have LP, and we know LP, what is LP, and with the norm P norm, that is simply a complete non-linear space, means Banach space. The LP norm is usual, which is given here, usual norm, and there is given another norm which has the following property. The norm, we don't know how it does it look or how does it assign other value, but it has the following property, that LP with that new norm is also Banach space, I mean complete, and has a property that if we have a sequence converges to F in that new norm in LP, then it is pointwise convergent also. Okay, then we have to prove that this new norm and our usual LP norm are equivalent. So to prove this, we will use two theorems. So basically the equivalency comes from the idea that you can define identity function. This is a trick that we can define an identity function from, let's say, LP to the new norm to LP with the usual P norm. Now the identity function is simply f goes to f. Okay. Now if you can prove that the identity function is isometry, meaning this is continuous and its inverse is also continuous. Look, if we can prove that identity function is continuous, then what we will get? We will get simply I of f norm P is less than equal to some constant times norm, but this is f, so norm P is less than equals to constant time norm. So we can get a constant that gives you the upper bound which is required for the equivalence. Now the lower bound will be get from if we can prove the inverse of the identity function is also continuous. So that is our goal, to prove the equivalence. And now to prove the inverse is also continuous, we can use bounded inverse theorem, right? What is the bounded inverse theorem? Bounded inverse theorem says if we have two Banach spaces and a bounded linear operator from one Banach space to other, then the inverse is also bounded if that is injective, a bijective map. Okay, may not be bijective but injective, then we can restrict the domain range to make it bijective, and then inverse is also continuous if the function is itself continuous. Okay, so this is the bounded inverse theorem. Now to prove, then we have to prove that I is continuous. Then we can, because these two are Banach, then its inverse will be also continuous, and we are done that these two are equivalent. So we will use in the end the bounded inverse theorem, but first we have to prove I is continuous to go into the bounded inverse theorem criteria, right? But how to prove the I is continuous? To prove I is continuous, we have to use a new theorem that is called closed graph theorem. Okay. Now first condition is needed to get the two domain and range are first, and this condition, you know that this is also Banach, is going to set up our the first criteria of the bounded inverse theorem. Now second criteria is the I should be continuous or bounded, same thing. So to prove the I is bounded, we need the second criteria, and second criteria along with the closed graph theorem will prove I is continuous. Now let's revise what is closed graph theorem. Okay, so let's revise it. What is closed graph theorem? This is MTA-6, right? as MTA-6. What is closed graph theorem? Okay, closed graph theorem. So basically, closed graph theorem. So let me write the closed graph theorem. Let's say if t from x to y is linear operator between Banach spaces. Okay. So x and y should be Banach space. then the following are equivalent. कौन से equivalent है? T is continuous or bounded, same thing. Number 2, graph of T is closed in x cross y product topology. Okay. The product topology given x cross y, the graph of T would be closed. Now what is the graph of T? The graph of T is x comma tx, this tuple, where x belongs to capital X. Okay. So we will use the condition to prove this. Okay. We will show the graph of T is closed, and by the closed graph theorem we will get T is continuous, where T is our I, X is our LP with the new norm, and Y is our LP with the P norm. Okay, so we write the setup. Okay, let me just it. Okay, so T here is our I, X is T is our I, X is our LP with new norm now, and Y is our LP with P norm. Now we have to use, now both are Banach spaces, that is given. I, to prove I is continuous, we have to prove that graph of I is closed in product topology. Now how I can prove the closeness of graph of I? So what is graph of I? Okay, what is graph of I is the main question. So what is our graph of I? So graph of I is x comma ix. Basically x means here f and I of f, right? This is our graph of I. Now we have to take a sequence to prove the continuity. No, but I of f is f again. So this is nothing but f comma f basically. Now to prove the graph is continuous, we have to take a sequence of points from this graph, and we have to prove that sequence converges again inside the graph. So we will take a sequence of point means Fn, right? Fn comma Fn, I mean I of Fn. That is the sequence from the graph. That is one point, I mean the sequence. Now what we can say? So we have to prove that we have to take that Fn converges to some point, let's say f. I mean we have to first take to prove, we have to take a convergence sequence, right? So you have to say that this converges to some f comma say f comma g. Then we have to prove that f comma g on that graph, right? That means f comma f means f equal to g we have to prove. Or basically if you just write without confusion, that is if. So you have to prove f comma if, that we have to prove. Okay, to prove the continuity of the graph using the sequence, we take a sequence, convergent sequence from the set, and the sequence is converging to some point. Eventually we say the point is inside the set, means every element that is in the closure of the set is inside the set. That is what we. But now the convergence in the product topology, this to this, implies convergence of f to f in the domain norm and convergence of if in p norm to g. But if is what? If is fn, ifn is fn. So this is converging to g in p norm, and this is converging to f in normal norm. Now look, given is what? In the question given was, what was given? If a sequence fn converges to f in p norm, and what we have assumed, fn converges to f in, our new norm. So we have assumed that our new norm, then fn converges to f pointwise. So this means limit n tends to infinity, fn k is equal to f of k. Okay, so this is what is given in the question. Okay, if fn converges to g in p norm, that also says pointwise convergence, that we know, and fn k converges to gk, but gk has to be equal to fk, implying g equal to f, and which implies our graph is closed. That implies I is bounded by closed graph theorem, which implies our 2 by bounded inverse theorem. These two norms, this and are equivalent. So all was about the properties you have to properly use in the right places, right? And that would give you the final result. So yeah, that is it. And you can try it, that if in p norm it converges, so it is also converges pointwise. That is very easy actually, so you can try. That was the main here that I skipped. So thanks for watching.